This video looks at the T-filter in GPC. So the previous video observed that a simplistic implementation of GPC could be highly sensitive to noise, and consequently there's a need to consider why this might be. We need to understand why first, and once we understand why, how can we make things better? Viewers will be unsurprised to hear that the most obvious thing to try is a low-pass filter. If I filter the output first, then hopefully it will filter out the high frequencies and therefore they will have less impact. And so this is in essence what early researchers did in GPC. It was found to be quite effective, and thus there was very little need to go beyond this for most cases, and you probably find the research on this stalled pretty much around the early 90s because people were happy with the progress they'd made. Let's just remind you then of what the sensitivity to the noise might be. If I just put the controller back into this block diagram so you can see what's going on, and if I assume that G is B over A, so if I had a loop something like this one at the bottom, then you could show that the sensitivity to a noise or disturbance signal coming in on the output is going to be something like this for the input, and that's the sensitivity we might be interested in. Now, sensitivity is linked to the compensator NK and the closed loop pole polynomial. You can see this, but the key thing is this is not particularly insightful. It doesn't really tell us how do I change the output horizon or the input horizon, or how do I change the weights, or how do I change the approach. And so it might be more effective to think about what GPC is actually doing, and therefore how noise might be affecting the proposed control action or the control law. So we're going to look at this from a slightly different way. Let's first of all summarize GPC in a few lines. First, you use a model to determine the predictions. You ensure the predictions are cleanly expressed in terms of what is known, that's past data in essence, and dependence on the degrees of freedom, usually the future control choices. You substitute the predictions into a performance index and optimize over the degrees of freedom. You implement the first of the optimum and repeat this every sample. And so the question is, where does measurement noise impact on this process? And hopefully it's fairly clear. Measurement noise comes in the first step. You're using a model to determine the predictions, and the predictions are affected by the measurement noise. So perhaps we need to go and look at that. So a summary. Measurement noise impacts on the predictions, and if you look at the predictions, what you'll find is if there was some measurement noise, here I've called it theta, you can see how it impacts on the predictions. Because the predictions are affected by noise, this in turn impacts on the optimum proposed input trajectory. So if this was your GPC control law, you can see this theta term comes in down here. And clearly, the bigger Q theta, the bigger the impact on the input signal. And so our target might be, how can we reduce Q theta? Because if I can reduce the magnitude of Q theta, then I'm going to make the GPC control law less sensitive to noise. Let's give a conceptual proposal then. What you might think is, I'm going to filter the output data before I use it in predictions, and this way the impact of any high frequency noise on the predictions should be reduced, because I've filtered out the high frequencies and then I predict afterwards. And you would hope this would have minimal detriment to the lower frequency dynamics, which are usually important. Now, there is a caveat that you'll see I've put here. The predictive control law and the performance index depend upon the actual output, not filtered outputs. So if you predict using filtered variables, you need to then go back to the actual variables. So we've given a conceptual step process down at the bottom here. You can see first of all, you take your output and you filter it with a low pass filter, so that Y tilde, in essence, you've filtered out some of the high frequencies. Then what you do, once you've filtered, you say, okay, next step, we need to form the predictions. But now the predictions are in this filtered domain. So what I'm going to have to do after that is some form of anti-filtering to get the predictions back into the domain that I actually want. And this is conceptually how early researchers in predictive control proposed to deal with noise. Let's see how we're going to do this then. First, define a desired low-pass filter as 1 over t. So I'm going to write that my filtered variable y tilde equals y over t, but you'll probably find it's more convenient to write this way. Ty tilde equals y. Now you note the relationship between the filtered and unfiltered predicted data can now be represented using the Toeplitz-Hankel matrices that we used for prediction in video 1. So I'm going to use this expression here, and I'm going to say, can I form a relationship between the future values? And this is it. You see, I get Ct y tilde future plus Ht y tilde pass equals C1 y future plus H1 y pass. So that's what was covered in the first chapter on prediction. Now, it's interesting to note that this C1 is just an identity matrix and this H1 is just 0. So you can simplify this to the expression that I've put down here in the orange box, which is slightly easier to use. And this is the last step we had in our process. How do we go from filtered predictions to unfiltered predictions? So you can see in this expression here we've got a link between the filtered predictions and the actual predictions that we want. So that was the last step. What about predicting with filtered data? Now it's straightforward to show that if AY equals BU, then similarly I could write A y over t equals B delta U over t, or AY tilde equals B delta U tilde. So in other words, the model that I can use to predict with AY equals B delta U, I can use the same model to predict with AY tilde equals B delta U tilde. So in other words, the predictions in the filtered domain, and you see it's exactly the same prediction equation that I used before. The only difference is I've replaced filtered variables with actual variables. Now this was the middle step in the process that we had. So you'll see we're sort of going backwards. So now we want to link these second and third steps. So what did we have? We had a relationship between filtered predictions and actual predictions, which was our last step. And we had, how do I predict in the filtered space? And what I'm going to do is say, can I put these two together and get something useful? So we actually want the future inputs and outputs in the unfiltered space, okay, to ensure we have the correct variables to use in our performance index. So this is what I'm going to do. I'm going to take the expression here in this orange box and I'm going to rewrite it like this. And you notice all I've done is I've multiplied throughout by Ct inverse, and I've separated the future filtered variables on their own. So y filter future equals Ct inverse times y future, that's the real outputs, minus Ht times y tilde pass. So that's the pass values of the filtered variables. And obviously I can do exactly the same thing for the future values of the input increments. Now, what I can do next is I can basically take these expressions and I can put this expression in here and I can put this expression in here. So where I have in the yellow box my vector of future predictions for the filtered variables, I can substitute in terms of the future real output and the future real input, and that gives me this box at the bottom. And it does look a bit messy, but if you pause the video and look at it slowly, you'll see that's all we've done, substitute in these two expressions. And now what we've got is predictions that are a combination of filtered and unfiltered variables, but this is exactly what we expect, and in fact exactly what we want, as you will see. So this top line is what we just had on the previous page, and all I'm going to do now is rearrange it slightly by taking this Ct inverse and multiplying both sides throughout by Ct. So you'll see I've got a Ct here, a Ct here, and a Ct here. Okay, and just as a note, if you understand how Toeplitz matrices work, Ct times H times Ct inverse is just going to be H, because H is also a Toeplitz matrix. I'm not going to prove that, but it's straightforward to do so. Now, if I rearrange what I've got, you will notice here I had Ct H Ct inverse, which is just H, so I've just got H delta U future. If I then look at the bits that depend on delta U tilde past, you'll see I've got a CTP and a minus HT. And if you look at the bits that depend on Y tilde past, you'll see I've got a CTQ and an t. And here's the nice thing. You'll see the future values are the real data. You'll see I've got y future and I've got delta u future. So all the future values, the values that I need to put in the performance index, are in the correct domain. So I'm happy with that. And all the past values are in the filtered domain. So it means I'm using filtered variables, so filtered out this high frequency noise, in order to form my predictions. So you've got a nice mix here. Filtered variables for the past, real variables for the future, just using a bit of clever algebra. So now if I tidy it all up and see what we've got, then you can write that the predictions are given by this expression here. So y future equals h delta u future, same as before, but you notice I've now got this p tilde delta u tilde past, q tilde, y tilde past, where p tilde and q tilde have these expressions down here. So I've got nice compact expressions for my predictions. Now, if you want to compare the predictions with and without the t-filter, you'll notice the future bit, I think there's a circle coming, here's the future bit, is the same, which is exactly what you expect. The effect of the future input is clearly not affected by filtering, and you should get the same mapping. However, what about the mapping of the past data? What you'll notice, instead of p delta u past q y past, you've got p tilde delta u tilde past plus q tilde y tilde past. So you've changed the mapping of the past into the future. So by filtering out the high frequencies, basically you're going to get a different mapping of the uncertainty into the future predictions. So in summary, GPC is quite sensitive to measurement noise, and thus it's logical to introduce some form of low-pass filtering of data before you do the predictions. Okay? And the sort of filter we've used is 1 over t. And a logical approach is to first filter, that's step 1, then predict, and then anti-filter to get the predictions back in the original domain. With a little bit of clever algebra, you can show this reduces to using prediction equations like this. Y future equals h delta u future plus p tilde delta u tilde past plus q tilde y tilde past, where p tilde and q tilde are given here, and the key thing is that the y tilde, you actually are filtering the data and you're filtering the input as well.